Hello, my name is Maxwell Goddard. I'm a major in biomedical engineering, and this summer I worked with Dr. G to try to create a new inorganic hydrogel. Hydrogels are gels which can expand to far greater than their original size when placed in water, and these gels have a variety of uses in biomedical engineering. Almost all known hydrogels are organic, meaning that they contain carbon, but inorganic hydrogels, or carbonless hydrogels, have the potential to solve a number of engineering problems in the biomedical field. So I tried to create a new one. This was done by adapting an existing method for making an organic hydrogel to try and create new hydrogels using the same overall process but different starting materials. The original process would take titanium diboride and mix it with a solution of tetramethyl ammonium hydroxide, which was 25% tetramethyl ammonium hydroxide or TMAH and 75% water by weight. After leaving these together for about 5 days and at a temperature of just under 100 degrees, this would cause the TMAH to remove the boron atoms from the titanium and replace them with oxygen from the water. This titanium oxide would then precipitate out of the solution in the form of nanowires, and once the reaction was completed and the resulting solution cleaned with ethanol to make sure there was no remaining TMAH, this nanowire solution could then be placed in water, and it would then form a colloid, which is a suspension in which the thing being suspended is evenly spread throughout and will not precipitate out under any circumstances, all except from a chemical change. The next step, of course, would be to induce a chemical change by adding a bit of acid, which causes the nanowire suspended to form a gel. Now, all I did was increase the time that these would be heated from 5 days to 7, and use different starting borides and oxides to try to create different metal oxide nanowires than just titanium. The first set of trials used pre-made nickel oxide nanowires that were purchased from Sigma Aldrich, and I reacted them at different temperatures and different concentrations of the reagents. This picture here shows three of these trials alongside water just to compare the potential colloids, as at this stage they are at what it was hopefully a colloid. Now, if the colloid was perfectly clear, which in this case it almost was, that doesn't mean it's not working. It just means that the colloid is not visibly different from water. And the only way to test for sure is to add acid and see if it forms the gel. In this case, however, they didn't. In the next couple of trials, I attempted to use iron boride and zirconium diboride. Once again, these vials are at the potential colloid step, and in front of each of the back row of vials that contain a large amount of the potential colloid are smaller vials that have only a little bit of our potential colloid, which had been centrifuged to make sure there was no refuse at the bottom, and then a couple drops of acetic acid were added. Now, while the resulting substance is stuck to the tops of the vials, which is a very good sign, as a hydrogel would do that, it would stick to the ceiling and the walls and it wouldn't come off even if shaken, which is why these are upside down. These came off after a pretty small amount of shaking. As such, they were not hydrogels. This was done at various different concentrations, just in case the concentration of 0.6 that was used in the original attempt that would create a titanium oxide hydrogel was not the right one for these different materials, and in no case did it create a hydrogel. Thus, it can be concluded that nickel oxide, iron boride, and zircon diboride are not good starting materials to create a hydrogel this way. It may be possible that only titanium works for this method, which, if so, is likely because when reacting to TMAH, the titanium comes out in the form of one-dimensional nanowires as opposed to a two or three-dimensional structure, which might be what's happening for our nickel, zircon, and iron. The only way to test that, however, is with a scanning electron microscope. So this is one of the future tests for future study, as it might give us some insight into why this wasn't working, as well as potentially more knowledge of the materials. It also may be worthwhile to try this with different starting materials like chromium diboride or vanadium diboride, as it might work for those. Either way, this, while not completely successful, still expanded our knowledge of potential methods of nanowire creation.